Students, and welcome to our fifth lab of the Introduction to Data Science course. In last few lectures, we covered some topics regarding machine learning that were and some basic algorithms like KNN and Bayes. And in today's lab, we would be actually using these algorithms to solve some real-world problems. The problem at hand is, and the problem that we would be solving in this exercise is MNIST, called MNIST dataset, which is a collection of handwritten digits in form of images, and you'll be using some machine learning, some classification algorithms to recognize these handwritten digits. So let's start. So in this lab, you're going to download this dataset from here and then unzip it in your current lab directory. Let's import some libraries first, then load the train part of the training set of the MNIST dataset. Let's see what this looks like. So as you can see, there are 4,000 columns. So actually this represents 4,000 images, and each image is a vector of 784. So there are 784 rows, and since images are two-dimensional, so this is actually each column is a flattened image. So this is actually a 28 by 28 image. So we can reorganize it into a 28 by 28 matrix to see the image. So let's first convert this data set into a matrix where we have 4,000 columns and 784 rows. The number of training set, the number of samples are 4,000. We can take any of the column of the array and reshape it into a 28 by 28 matrix, so you would get one image. So let's try the first one, the 0th column of the 4,000 columns, and let's see what this looks like. So as you can see, this looks like a handwritten digit which might either be 3 or 5, but it's not very clear. So this what the purpose of this lab is, we have to recognize these images, convert them into digits. And let's try another image. So this clearly looks like a 3. In the next step, we would create a 10 by 10 array of first 100 images and show it below. So we would actually want to display the first 100 images of this data set. So let's do this. I've already wrote the code, so let me paste it here. So we generated an image. The size of the image is 15 by 15. We have 10 columns and 10 rows. So each unit of this 10 by 10 matrix would be an image. So let's first take the first 100 images by extracting the data of the first 100 columns. Then for each of these image, we would reshape it to a 28 by 28 matrix, and then plot it as a subplot, and then show the image. So let's run this. It will take a while. Let's wait for it a bit. Okay, here we have it. So these are the first 100 images, and you can see some of them are very easily recognizable by the naked eyes, and some of them are a little bit confusing. Okay, so let's then first compute the distances between the training images and the test images. So let's first if a test image and remember that all these images in the training set are labeled. So for example, if this image which looks like 6, so it also has a label which says 6, but the test set are all just a bunch of images with no labels. So we want to calculate the distances between each test image and each train image, and the one that is nearest in terms of the distance to a train image we would use the label of that train image for the certain test image. Okay, so let's run this. So we have 2000 test images, And to calculate the to use the distance, we will be using a squared Euclidean distance, which is basically x minus y dot x minus y, and if we open this up, it's x square minus 2 xy plus y square. So we can calculate these dot products product first individually, and then subtract this term from it. So let's first calculate this dot product, which is x square, and then we calculate the dot product for another dot product, which is y square, and then put them in the distance formula, which is x square plus y square minus 2 xy. So if we check this dot shape, as you can see, this is a 2000 by 4000 matrix, so which means that for each test image among this 2000 image, there is a distance calculated from each train image. So there are 4000 distances for each test image. Okay, then we can produce the normalized distance matrix, that is by dividing the distances by a standard number, so that they are normalized instead of these. If we calculate, let's see the distance between the first test image and the 10 train images, they are very big numbers, so we want to normalize them. And the normalization is basically pretty easy. We already calculated x square plus y square, so you just have to divide each number by x square plus y square. So np dot divide, we want to divide each value. So this and np dot sum x dots y dots. So each value from this distance matrix would be divided by the corresponding x square plus y square. So let's run this. Okay, now we have the normalized distances. Okay, now among these normalized distances, we want to order them by ascending order, so that the smallest distances are in the beginning. To order them, we use arc sort. So we would sort these normalized distances, and let's see. So you can see these are now ordered. So as you can see, these are now the indexes of based on their ordering. So for example, the 1673 train instance is at least distance at a minimum distance with the first test instance. So it's the first one in this. So we can use these new indexes to actually order our predictions from the training set for our test set. So let's say we want to check the appropriate label for the first test instance, that's the 0th. So we would calculate the distance, the normalized distance of the first test element to the train instances. So as you can see, these distances are in the ascending order, and we can use these new order distances to actually predict the labels. So as you can see, these are our labels now for the first test instance. So as you can see, the first few labels are all 7, and then as we move away from in terms of the distance, the labels are also changing. So to answer the first question here, to this part, the label that is best matched for the test point 0 would be the label 7. Now up till now we can actually have just an idea to show a few to see a few nearest train instances, and then use the labels of those nearest train instances for our test instance. Let's formulate this in a formal way. So let's use k is equal to 3 and use k nearest train instances as our ideas, as our predictions for the labels. So for k is equal to 3, we would calculate kn labels, that is labels which the first 3 or the nearest 3 train instances would be used to label our test instance. So as you can see in this in this matrix, the first 3 for the first test instance, the first 3 labels are 7. For the second test instance, the first 3 labels are 2, and so on. And sometimes they would be different than each other, so then we can use majority voting and so on. So let's do some more exercise. So let's try to calculate the votes for each of the test instance, where we would be for each test instance we would be counting the nearest train instances, and the majority vote would decide on our prediction. So let's write this code here. We can use a for loop. So we can use a for loop to populate this vote matrix. Okay, so for each test instance, we would calculate the kn labels. That is, for the vth row, we would use the labels of the k nearest neighbors, so that is up to k, and then if those votes would be used to populate the unique values for the votes. So that's why we are using return underscore counts as true. So we'll be just using the counts of each unique value. So let's run this. Okay, let me define k first here. So let's let's use try 5. Okay, now we have calculated the votes for each test instance, and then among the votes we would be using majority votes, so use argmax, and that would give us the best labels for each test instance. So now we have 2000 labels. Okay, let's see if our predictions are right. So we have the labels for the test instances as well, so we need to compare our predictions to the actual labels, and then if the predicted label is equal to the actual label, we would count it as 1, and if they are not, we would count it as 0, and then calculate the mean. So that would give us an accuracy. So here you can see the accuracy is 91.35%, which is pretty good. But let's see if we can change this accuracy, if we can improve it by using some different values of k. So remember from the lectures, the value of k is extremely critical. So as you can see, there is some problem with the code. Let's put this code to calculate the votes here as well. Okay, now let's run this. Okay, so our accuracy is almost the same, it's not much different, but it seems like it's not improving. So we can actually try to see to calculate the best value for k by trying different values of k, let's say from 1 to 10, kn in range to 11, and then let's paste this code here with a bit variation. Okay, and okay, okay, -1. Okay, let me initialize accuracy in p dot zeros. Okay, and let's plot this. Okay. Okay. Okay, let me make it one dimensional. And okay, okay, so as you can see, with different k there are different accuracies, and you can see we get the best accuracy is k equal to 4. And before k equal to 4 the accuracy is a bit lower, and after k equal to, even for k, increasing k the accuracy is again getting lower and lower. You can also see it from here, the accuracy vector. Okay, now let's try another thing. Let's try, instead of using voting and then counting the taking the majority as vote, let's use the inverse of the distance as the vote. So if a trend sample, if a trend instance is nearest, if some trend instances are nearest to a test instances, instead of counting them, we would actually use the vote as the inverse of the distance. So if so if there are like 3 trend samples of with same labels nearest to a test instance, they would get more voting technique. But if we use inverse distances, then even if there is just one instance, but if it's more near, if it's as compared to the 3 which are the same, then it would get more weightage. So in that case we would be calculating or we would be populating this vote matrix by the inverse distances of the nearest samples. So let's first do this. So as before, we are calculating the nearest, we are determining the nearest labels as previously, but now while populating the vote matrix, we are doing that by using 1 divided by n distance. The rest is the same. So let's do this now and calculate the accuracy. Okay, it's not n votes, it's votes here. Okay, so now for k is equal to 3, we got accuracy of 0.891. Let's try another k. Let's try k is equal to 4. Okay, so now we have a different accuracy. We can also, as before, try for these for different case. So let's paste the code from here and then change it as per our new settings. So now the only difference is in how we calculate this vote matrix. Okay, the rest are the same. There is not much difference. Okay, let's check it. Okay, it's good to go. Okay, let's make it K. Okay, this is also K. Okay, and as you can see, let's okay, when we are using the inverse distances, so because just use the nearest, only the nearest training instance, so it doesn't matter if we change K. Okay, probably a better algorithm would be to use both votes and the inverse distances, so that when you counting votes, so instead of using one instance as one vote, we can multiply each vote by the inverse distance. So the nearest samples would get more vote weightage, and distant samples would get less weightage. Okay, so that's so far okay for the k nearest neighbors. Now let's move to the next part of the lab, which is naive Bayes. We'll be using now naive Bayes algorithm to solve the same problem in the MNIST dataset for digit recognition, handwritten digit recognition. Okay, so before we move further with the naive Bayes, first we need to install this library, and then we want to change our data to a binary data set. That is that in the original data set we have each training or test instances are actually 28 by 28 images, where each pixel has a certain value between 0 and 255. But now we want to change these values to binary values, such that if a value is greater than 128, it would be changed to true or 1, and if it's less than or equal to 128, it would be changed to false or 0. So now in the new data set we only have zeros and ones, or trues and falses. Okay, so let's create this new data set, and then we import the naive Bayes classifier from the sklearn toolkit. Okay, then we fit our model on the training data, and then we use the model to predict the labels for the test data, and then at the end we would calculate the accuracy by comparing our predicted labels to the actual labels. So as you can see, the accuracy is 0.78, which is far more less than the accuracy which we got from KNN. Okay, so using this analysis you can give answers to these questions. The accuracy of the naive Bayes compared with KNN classifiers on this data, which is 0.7805, and it's we can't do anything. Actually with KNN we could change the value of K to change the accuracy, but here we can't do much. So this is our base accuracy basically. And this accuracy also tells us that the basic assumption about naive Bayes, which actually where we assume that all the features are independent of each other, is not completely true. Otherwise we could get a higher accuracy. Okay, so you can answer these questions in the response form. Okay, to check the overall performance on each individual digits or each individual samples, we can use confusion matrices. So this code would actually define confusion matrix, where on row wise we have the actual digits, and column wise we would have their predictions. So if a digit is correctly predicted, we would get a higher value on the diagonal for that certain digit. So let's calculate this confusion matrix. So as you can see, we usually have higher values on the diagonal. This is the for example, this value means that the digit 0 is correctly labeled 85% of the time. The digit 1 is correctly labeled as 95% of the time. Digit 2 is correctly labeled 75% of the time, and so on. Okay, we can actually also visualize this confusion matrix, but because the values are all between 0 and 1, so let's first change them to 0 to 255 by multiplying this matrix by 255, and then we can visualize this by plotting a grayscale image. So let's calculate this new confusion matrix, which is conf multiplied by 255, and then okay, let's see this. Okay, you can see we have the visualization of our confusion matrix now. Okay, let's make it a bit bigger. Okay, as you can see, now it's color coded image, and the intensity of a color actually shows its high value. So as you can see, these two values, as we have seen in the confusion matrix, has higher these two values were high, so they have more brightness. This one is a bit dark, so this means this is a low value or a small value. So let's try to answer these questions. So which digit is most misclassified most often? And so if you can see, from here, this digit is either this one, which is 5, or this one, which is 8. So let's see the actual values from the confusion matrix. So from the confusion matrix, the correctly labeled digit for digit 8 it's 0.61, this value, and for digit 5, 0, 1, 2, 3, 4, and 5, it's 0.78. So as you can see, this 0.62 or 0.6197 is shows that digit 8 is misclassified the most, and you can answer these questions here. Okay, let's see this last question. How many mislabeled pairs are there? A pair of correct digit with incorrect label, which has a probability of greater than 0.05. So it's very easy to check from the confusion matrix. You can see the confusion matrix has these values, and all the off diagonal values actually represent the mislabeled pairs. So if an off diagonal value is greater than 0.05, you can count it as a miscorrected pair, and counting all such pairs would give you the number of miscorrected pairs from the confusion matrix. So let's calculate this. Create a matrix where on the diagonal we have zeros and all the other values are ones, so that we can multiply it with the confusion matrix to remove the diagonal values. So np.ones 10 10 and okay, np.diag np.fill underscore diagonal a with zeros, and okay, let's check. Okay, yeah, this is correct. Okay, now let's calculate, let's call it miss and probabilities is equal to np dot multiply f, just multiply this with a, so here you have all the probabilities for the pairs, misclassified pairs, and so we can check if any of these probabilities are less than 0.0 greater than 0.05. np dot unique p greater than 0.05 and return underscore counts is equal to true. So for the values which are greater than 0.05, there are 11 such pairs. So you can see there are 11 such pairs where the probability of misclassifying them as incorrectly classifying them is greater than 0.05. Okay, so that's all for today's lab. You can return your responses by clicking here. It will open Microsoft Forms. You can fill the answers to these questions here. In that forms there are 8 questions, and then you can submit it by Tuesday. Thank you very much.